So good evening, everybody. Welcome to the 944th meeting of the Amateur Telescope Makers of Boston. We have a pretty packed business section of the meeting. So without further ado, I'm just going to slide right into that. Just want to make sure this is good. Okay, so here we go. So the agenda is the same agenda you see every month. And so I'm not going to go through it since you already know what it is. This is Glenn Chappell's work, courtesy of Julie Kaufman. I actually thought this was a pretty funny cartoon because I feel like this is me all over. Groceries, just enough. Clothes, just barely. Household items, whatever. Cheapest. Astro stuff, throw the money in the air, right? Anything to say about this, Glenn?
Says it all.
It says it all. I'm sure out there somewhere there's a 12-step program for all these, gadgets that we're all buying, but that can't be possible.
Well, there's already AA, Alcoholics Anonymous, so we'd have to have a new abbreviation.
Yeah, be careful here. Be careful.
SGA, Stargazers Anonymous.
There you go. Perfect. All right, look, onward, Glenn. Here's your quote.
Black holes are where God divided by zero, and that was a statement from Albert Einstein.
Very good. On to the observer's report. Why don't you go ahead and do these, and why don't I do these, and you can talk about the object of the month. How's that?
Sounds like a good thing.
So it's cloudy and raining out right now, and we're in the middle of a meeting, so you're not going to see Venus past 4 degrees south of the moon tonight. But if you want to see Venus, look low in the west right after sunset. The ecliptic at this time of year, of course, is running low across the west to the southwest. And so during this apparition, Venus is not going to get very high above the western horizon. As you always hear me say, I think the best time to look at Venus is in the daytime. And so that perhaps is an observing challenge for you. On Saturday, the 11th, asteroid number 2, Pallas, is at opposition, magnitude 8.6. Next Tuesday, Mercury reaches greatest elongation east, 27 degrees away from the sun. Again, difficult to see in the west because the ecliptic is so low. Neptune's at opposition on the same night at magnitude plus 7.8. We were at the clubhouse on today. Was it? No, it wasn't. Steve Clarity, where were we there? Last night or the night before? I saw Steve. Well,
yep. Two nights ago we were there.
2 nights ago, yeah. Right. And we looked at Neptune through Steve's 18-inch scope, and we were treated to a view of Triton, the large moon of Neptune. So that's kind of fun. If you have an aperture, you might want to check it out. It's about 14th magnitude, 13.6. It's a tough object, but you can see it. Anyway, variable star Algol reaches a minimum brightness next Wednesday at 9:40 in the evening. That's a pretty rapid drop in brightness and a rise back up again, a few hours. Glenn likes to talk about getting out there and plotting it, and that might be something you want to do. On Thursday, Saturn is 4 degrees north of the moon, and the following evening, Jupiter is also 4 degrees north of the moon, and I couldn't fit it all on one page. Next Wednesday, Wednesday the 22nd at 3:21 p.m. is the autumnal equinox, and as you've already sensed, our evenings are getting longer. The darkness is getting longer, and so it's one of my favorite times of the year. Interestingly, on Thursday 9:23 and Thursday 9:30, Mercury is 1.5 degrees south of Spica at sunset, once moving away from the sun and once on the way back. And Astronomy Day is Saturday, October 9th, when Venus will be 3 degrees south of the moon. And those are some things to look forward to. Glenn, go ahead with the observer's challenge for the month.
Okay, think I got my voice on.
You sound good.
Getting back to Algol, it's still a little low in the sky for some of its minima, but in the months coming up, it'll be up there high enough to be able to see the start of an eclipse and the end. And again, we've got our fingers crossed. I just wanted to go back a bit. I was talking about visiting a lot of these websites, and I was going through the California websites, and almost everyone had a COVID alert. And basically the message was just getting worse. We may have to backtrack and go back. I'm hoping that doesn't happen. I would like to have a club get together to observe one of these eclipses of Algol. It's kind of an interesting event, but again, let's just cross our fingers that the things don't get worse. We're just getting back to we can start to do things, and we'll hope for the best. Anyway, the target for this month was a combination NGC 6823/20. It's a cluster and an emission nebula, and it's about midway between the star Alpha Vulpeculi, which is just, Rich can point that out, it's a little below Albireo. Oh, I've got it right here. Okay. It's a little bit below Albireo. There's Albireo. Alpha Vulpecula is right here. And Alpha is actually a wide double star. It's actually a combination of Alpha and the star 8 Vulpeculae. And it's midway between that and M27 right here. It's about 3 degrees between each.
Glenn, let me advance the slide real fast.
Sure.
So here's that slide I was telling you about,
go.
Glenn, with Albireo here, Alpha
Yep.
Vulpeculae. I couldn't have pointed to it if I had to. And here's the cluster and the emission nebula in question right there.
And I would guess NGC 27 is somewhere down around here. It's not that far off.
Yeah, it's off
But
the map a bit. But the reason
when
I
I-
wanted to put this one on is because if you notice, I set the Sky
Yeah.
Safari Pro for a limiting magnitude of 7.5, which is a reasonable magnification for a finder scope. And I noticed that a nice little asterism here, this V-shaped asterism right here, where the cluster is very near the base of that long, almost isosceles triangle. And I thought that this would be a nice star hop from here to this asterism to here. From this cluster to Alpha Vulpeculae is 3.5 degrees, which should fit in a nice 8x50 finder scope nicely.
And if you notice again, Alpha Vulpeculae, there's that extra star, 8 Vulpeculae right there. And if you key on that, once you've gone from Albireo to Alpha Vulpeculae, you got the orientation of the field as well, so you know which way to travel. We'll go to the next slide now.
Perfect.
And here it is. This is an AVSO chart. And there's Alpha Vulpecula in the upper right there. And you can see the travel. And I think Rich will point out, I see my cursor, but can you see it there?
No, you shouldn't, because I'm controlling this. So
Okay, yeah, I got
your cursor does you no good.
All right, if you look at where the X there for NGC, and you see just to the right of it, there's that little chain of stars. And as I was star hopping from Alpha Vulpecula, that was a very striking sight. They're about 9th and 10th magnitude, maybe a half degree across. But it's a nice little group that also homed you in on NGC at 68, 23, and 20. We'll go to the next slide.
If I can get this.
I think
thing
we
to
have some
work. There we
images.
go.
And
So this is by Doug Paul.
Yeah, this is Doug Paul's, and it's a wide field view. And Rich will point out again that group of stars. It's
There
over
it is
yeah,
right
right
here.
there. And there's an extra star that was just out of the field of view. That's just a nice little chain of stars. And the cluster is a little bit, it's not really at the heart of that nebula, it's out to the side. And Rich will also point, there is a pillar, if you will, a dark pillar that really dominates that group. There's some of them, it's very much like Messier 16 with the pillars of creation. The thing is, the nebula itself is very large and faint. And this whole unit is about 6,000 light years away. The cluster itself, and Rich will point that out again,
It's right here.
it's about 50 light years across. It's made of a lot of young stars. In fact, it's dominated by a wide double star. And I looked in the Washington double star catalog, and the spectral class for the brighter star is 06. That's a really hot star. And a lot of these stars are O-type stars there. I saw about a half dozen stars that were around 9th magnitude, 9th and 10th, and then it dropped off to just a sprinkling of 13th and 14th magnitude stars. The cluster I wasn't even able to see at all, even with a nebular filter, so I'm not sure. My guess is with that, you'd probably want to go to a wide field eyepiece because this thing is about 40 arc minutes across, 40 by 30 arc minutes. So it's full moon size or larger. So you'd want to probably go to a medium power, low power, wide field eyepiece and a nebula filter. And I would definitely get out in the country. I don't know if anybody can report having seen this visually. And
Let's
we'll go to
let's look at Mario's picture.
Yeah, Mario's a close. There's some more of those pillars of creation. And Rich will point out the cluster in the middle, the bright cluster.
Well, here it is right here.
And the two double stars, you see those two stars
Here?
right there? That's a double star. And I did see a couple of stars between them with my 10-inch
Mhm.
telescope. But you can see there's a handful of really fairly bright stars, and then it fades off pretty rapidly. The bottom line for visual observers is it's a kind of a neat cluster. Again, I like that chain of stars that you see as you're going toward this cluster. And I would encourage anybody to see if they can make a visual observation of that nebula, because it was very tough. It landed with my telescope in magnitude 5 skies. So that's about all I have. So keep looking out.
From my experience, when you see a red nebulosity like that, it's H alpha. And I think the ultra high contrast narrowband filter works the best, as opposed to the Oxy 3, which zeroes in on the line of oxygen in the green part of the spectrum. And these O-type stars here are undoubtedly what are illuminating this entire nebulosity and causing it to fluoresce. Yeah, pretty cool. All right, so go out there and see if you can spot this. Get those filters out, get to dark skies if possible. And I think that's the last slide, Glenn, right?
That's it. Thanks a lot, Rich.
All right. Tonight's speaker is Richard Nugent. I thought it would be fun to have somebody named after me or named same as me to give a talk to the club on president. So Richard and I met back he and I have communicated by email for a while, but I met him in person at NEAF a few years ago, and Bruce Berger bumped into him on the eclipse flight that Kelly and Bruce went on. And so I got in touch with Rich, and he said he would be more than happy to talk to us. He's from Houston, Texas. He's part of the International Occultation Timing Association. And Richard graduated from the Department of Astronomy at the University of South Florida / University of Florida in 1979 with a BS and an MS in astronomy, specializing in positional astronomy. His graduate work was with the world-renowned astronomer, astrometrist, I practice saying that all day, and the father of modern astrometry, Heinrich Eichhorn. Richard's career at NASA's Johnson Space Center in Houston, Texas, included analyzing satellite data, and in the Space Shuttle program, flight design, rendezvous maneuvers, and instrument pointing to celestial targets, along with military applications. Richard has traveled worldwide on over 150 scientific experiments, collecting scientific data on solar eclipses, plus stellar eclipses by asteroids, which are affectionately known as asteroid occultation. The reason I asked Richard to speak with us tonight is because they make it very, very simple. The IOTA makes it very simple to record these occultations of asteroids passing in front of stars. And I wanted to kick off a period of time where I try to inspire folks to think about doing citizen science with not only the Middleman ATMoB Observatory, but the Bill Toomey Observatory as well. So Richard, I gave you co-host privileges, and that should allow you to share your screen. So I saw you, and so why don't you go ahead and take it away?
Okay. How's that?
That so far looks pretty good. It says your screen sharing, and there it is. So you have full control over the program, and you can click as you need to.
Okay, thank you very much for the invitation to speak, Rich, and to the group. And I'm going to talk about the introduction to occultations. I'm with the International Occultation Timing Association, and our website is occultations.org. And asteroid, I spelled asteroid wrong here. I just noticed this. It's really asteroidoccultation.com. I'll fix this on the next presentation. Okay, what is an occultation? This is an example of the moon occulting stars in the Pleiades star cluster. As you can see, stars get covered up and they reappear. Disappearance and reappearance. This is obviously not in real time. This takes several hours to happen. So occultation basics, what is an occultation? It's when one celestial body passes in front of another, momentarily blocking its light. This could be the moon passing in front of a star or an asteroid. The asteroids passing in front of stars. And if you want to talk about it even further, I mean, a solar eclipse is an occultation where the moon passes in front of the sun. When a planet passes in front of the sun, you know, Mercury or Venus, that's a transit, but they also have separate terminology. Now, occultations have been used in the past. This is by historical seamen to determine position at sea. And the way they did this, the occultation on one side of the Atlantic Ocean is going to be at a different time at the other side of the Atlantic Ocean because of the three-dimensional view of the moon with respect to the star background. It's used to help refine the lunar orbit theory. We've determined the lunar limb profile, which is the edge of the moon, the craters, mountains, and valleys. And it's also in the hot topic these days is determining size and shape of asteroids. Okay, some of the discoveries from occultations, not all of them. The moon was found to be spherical, but slightly oblate, just like Jupiter's very oblate. The Earth has slight oblateness. Double stars down to 0.003 arc-second separation. The rings of Uranus were discovered in 1977. A lot of people know about that. The atmosphere of Pluto was discovered in 1985 by the occultation technique. Titan's atmospheric properties, that's one of the moons of Saturn. And to date, we have over 10,000 asteroid sizes and shapes from the asteroid occultation technique. Asteroid moons have been discovered by occultations. Stellar diameters can be determined from occultations and optical identification of radio sources. This is when the moon passing in front of a radio source. You can pin down exactly where it is. Now, this is an example of an occultation of a double star. It's an animation. And as you can see, this is the moon about to cover up a double star. And because of the orientation of the two stars, one star gets covered up first, then the second star. So what does this look like on the light curve? On the left-hand side here is the light curve of this event. This is a real object. You have the total light level of both stars up here. You can see my cursor. Then the first star gets covered up, and the only light remaining is from the second star. The second star gets covered up, and then the light level goes down to 0. Now the fluctuation in the dots here, each dot is one video frame, which is 0.03 seconds of time. This is due to the Earth's atmosphere and the seeing conditions. So this happens all the time. All right. Okay, next slide here. Okay, this is a paper published in the Journal of Double Star Observations. This was, I believe, 3 years ago, of a double star discovery. And a lot of papers by Iota get published in the Journal of Double Star Observations for these kind of discoveries. Here are the light curves made by the observers for this discovery. Steve Messner, John Moore, Paul Maley. The top light curve, you can see the total light of the star, both stars. Then we have a drop in brightness when one star gets covered up. Then a total drop in brightness when both stars get covered up by the asteroid. And then when the asteroid is completely covered up both stars, it comes back up in reverse order. This happens for all three light curves. Now with the moon, the previous animation, the moon can cover up a star and then pass over completely, but you have to wait an hour for that to happen. Who's got that kind of time, right? Okay, this is this particular double star discovery. The primary star is right here, and the secondary star is right here. Now, position angles are determined in separations by this technique. It turned out this particular double star had a separation of 0.0143 arc seconds, give or take 4/10,000ths of an arc second. This is less than 2%, this 2% precision. And the position angle of the secondary star, 73.6 degrees. Position angle on the diagram here, north to the top, 0 degrees, east is 90, south is 180, west is 270, and so on, and back to 0 or 360. So many double stars have been discovered by this technique. Now, on another orientation of a double star, let's say they're not oriented favorably, but they're oriented basically north-south, 0 degree position angle. The moon covers them up, and they both disappear at the same time. So as you can see with the light curve, you can't really tell if there's a double star here. So the position angle of the stars is very crucial to make a discovery or confirm an existing double star. Okay. Now, another thing that occultations can discover is the stellar diameters. In this animation, we have the first star, the white star, gets covered up by the moon, very small star. Then a red giant gets covered up. And you look at the light curves on the left, the top light curve, the very, very small star, instantaneous disappearance of the star, okay? The large red giant star, a gradual disappearance in light before it gets completely covered up. And this delta T here from the beginning of the occultation to the end when the star is completely covered up, this can allow us to determine the diameter of the star if we know its distance, because we know how fast the moon is moving, or the asteroid in that case. And I believe the next slide is this is an example of an asteroid occultation of a very large star. Now, for some reason, the videos won't play on PowerPoint, so I'm going to momentarily get out of PowerPoint and show the video. Got it. Let me back up. There's the disappearance and then the reappearance. Let me go do this one more time.
So this one's obviously an asteroid occultation.
This is an asteroid occultation, a gradual dimming of the star and a gradual reappearance. Okay, let's go back to the PowerPoint.
And that's in real time?
That's in real time, yes. In fact, the lower left-hand corner is the universal time, hours, minutes, and seconds, and fractions of a second with a GPS time insertion. We'll talk about this later. So there it goes again. We'll do this one more time. And okay. Okay, back to PowerPoint.
How wide was the path on that occultation? Do you remember?
I've got the
the ground track.
It approximately 70 kilometers.
Mhm.
Do we see the PowerPoint screen back?
Not yet.
Not yet, okay. Share screen.
Here it comes. There it
Okay,
is.
I think I got it. Okay, here we go.
Perfect.
And that's full screen. Okay. Yeah, this is the profile and shape of the asteroid. Here's the light curve of the occultation. You can see the gradual dimming. Took 33 video frames to go out and 33 video frames to go back in. So what I did was using the distance to the star and the speed of the asteroid at the time of the occultation, I did a back of the envelope calculation, figured out that this giant star was 50 times the diameter of the sun, give or take plus or minus 10. So that's just my back of the envelope calculation. Okay,
Nice.
let's move on. Okay, let's take a look at this next animation. You see multiple disappearances here, then a long disappearance, then multiple disappearances again. Everyone saw that? So what's going on here? This is not exactly real time. This is probably 10 times faster. This is the light curve of that particular event. We have several drops in brightness on the left-hand side, alpha, beta, gamma, delta, and epsilon. This is the pre-immersion of the main occultation. This is the post-immersion of the occultation. And on the right here, these are the actual strip charts. I photographed these at the National Air and Space Museum in Washington, D.C. These are the actual strip charts for that particular occultation. Again, several drops in brightness going in and going out. So what's going on? By the way, the one on the left here was published in Sky and Telescope magazine. This is straight out of Sky and Telescope magazine. And if you've already seen it, it says here kilometers from the center of Uranus. So you kind of know what's going on here. This is the discovery of the rings of Uranus in 1977. So this is what really happened. As the rings passed in front of the star, multiple drops in brightness, the planet passed in front of the star, reappeared the star, and on the other side of the rings, more disappearances. I was in graduate school when they made this discovery. It was very exciting, pretty cool. And I was already doing occultations back then. Okay, now let's move over to lunar occultations. Lunar occultation geometry is very simple. The moon casts a shadow on the Earth, if you will, defined by the shadow you see on the surface of the Earth. And along the lines N and S, which is the north limit, south limit of the moon, you can see the shadow moving across the field of view. Now, if you're observer at A or observer at C, you will see what is known as a grazing occultation. In other words, the moon grazes by the star. If you're at position B, anywhere along the path B, you'll see a total occultation, just lights out, and maybe half hour, an hour later, it reappears. So it looks something like this. B is a total occultation, A and C are grazing occultations. And as you can expect from a grazing occultation, the moon's surface is not smooth. It has craters, mountains, valleys all over the place. So the lunar limb, the edge of the moon that we look at, might look, okay, this is another video of a total occultation. Get out of this, bring this up. We see the video?
Yep.
Okay, this is two occultations covering a time period of 12 seconds. The first occultation already occurred. The second occultation is this star right up here, this faint star. And we'll play this again. It's kind of like a horse race to see who gets in first. As it repeats, the first star is down near the lower center of the screen, right down here. This is actually at a club star party. I showed this video. I made this observation. There's a second star right there. So now, in addition to seeing the occultation, you'll notice at the bottom of the screen, you see a bunch of numbers. On the lower left is the hours, minutes, and seconds, 2 hours, 37 minutes, 25 seconds, 6 seconds, and so on. And on the right-hand side, you see that very fast-moving set of numbers. That's the fractions of a second. On the far right is the video frame number. So we can pause this video and just play it back frame by frame if we want. We don't really use this program, Windows Media Player, to replay these videos, except for presentations. We have special programs we can play back frame by frame and read off the exact video frame of disappearance. So we get very accurate times. Okay, let's go back to PowerPoint.
And that always seemed to be that always seemed to me when it came to timing occultations was to be able to really nail down the time.
Exactly, that's what we want to do. Okay, we back to the PowerPoint screen? Visible?
We are. Mhm.
Okay, let me get it going here. Okay, that was just a screenshot of the video. Now, grazing occultation looks something like this. Because of the lunar profile, craters, mountains, and valleys, the star will disappear and reappear several times. Again, this is speeded up by at least a factor of 10, maybe 20. Typical grazing occultation window would be 3 to 5 minutes. Now, this again is not to scale, but the moon's limb, which you can see is not totally smooth, is projected onto the Earth's surface. This is Central Texas, where I live. And you can see how the limb projected on the surface. What we do, we set up observers perpendicular to the path here. Here we have 5 observers. So we'll just see what happens with each observer as they make their here they are in some country road. By the way, this is a country road leading to the Texas Star Body. Here's what they're going to see. Observers 1 is going to see the most number of events, observer 5 the least, as the moon's limb passes in front of them, covering up the star. Something like this. Again, much highly speeded up. So this is what they will see. Observer 1's on the bottom, observer 5's on the top. This is what they see on their videos. Disappearances, reappearances. Okay, so if we take the data and plot it out, we get something like this. Observer number 1 had a disappearance over here, reappearance over here, another disappearance here, reappearance here, disappearance. We had 3 long occultations, a short occultation here, 2 long occultations here. Observer number 2, 2 total occultations. Observer number 3, only 1. Observer number 4, only 1. Observer 4's occultation is a little bit shorter because it's closer to the top of the mountain. Observer 5 saw nothing. Observer 5 is a very important observer because it puts a limitation on the height of the lunar mountain at that point. So again, if we plot the data, this is what we get, the size and shape of the lunar limb. And this was done back in the 60s, 70s by amateurs all over the world. And timings were made by, not video as we have now, but by stopwatch and other methods. Excuse me. Now, this series of pictures here, we have a guy named Charles Watts back in the 50s. He scanned pictures of the moon's limb to determine the size and shape of the mountain ranges, mountains, craters, and valleys by scanning these images using this contraption over here called the scanner. This is what they had back then. And it would create a strip chart here on the right-hand side of the exactly what we saw before, the shape of the lunar limb. And what he did was he made these charts called the Watts charts, named after him, Charles Watts. And in this chart here, the solid line here is his prediction of the moon's limb by making the scans of the photos, okay, for that particular longitude on the moon. These solid dots is what we probably the equivalent of sea level on Earth, the mean level of the moon. Excuse me, the unfilled circles, the circles without fillings, are actual observations. These are made by visual observers using stopwatches. And they're pretty close, but not exact to the Watts prediction of the profile of the moon at this point, but reasonably okay considering visual. Now, along comes the Lunar Reconnaissance Orbiter launched about 15 years ago, did extensive radar mapping of the lunar surface. We have highly accurate elevation and topography of the moon to unprecedented accuracy to something like 10, 15 meters. So the exact profile of the moon looks like this with the lunar length, the radar mapping. And the Magellan spacecraft did this with Venus back like, what, 25 years ago, 30 years ago? This is the same thing except on the moon. So we do the occultations and do the comparison. On the left, for this particular profile of the moon, we have the visual observations, which somewhat match, somewhat the Watts data, the Watts profile from the scanned images of the photos. And on the right, the Lunar Reconnaissance Orbiter satellite data with video observations with time insertion. These observations, you can see, are right on, exactly on. So this is done to generate a very, very accurate profile of the lunar limb, which we use for solar eclipse purposes. And that's a whole other story to predict Bailey speeds. Again, a whole other talk. I'll just leave it at that. Okay, these are some of the timing strategies, including historical strategies using for measuring occultations. We have the stopwatch method, which nobody uses anymore. Eye and ear, in which you just basically memorize the time and you write it down on a piece of paper. A recording assistant, a second person that hears your call outs. Internet and computer, people are using it these days, starting to use it. I've never really liked it due to the processing delays and getting a computer to read data times and so forth. Tape recorders have been used, of course, with WWB radio. CCD drift scan, I have a slide on that. Video, very good, yes. These are the precision accuracies we can get. And time inserted video is the best, 0.03 seconds of time accuracy. On the right-hand side, something called personal equation. This has to do with the errors associated with this technique. Video techniques, CC drift scan, there's no personal equation because these are not visual techniques. The other techniques, there are some problems here. So anyway, this is the 21st century. Everybody uses time inserted video. And in the past, recordings were done with WWB radio, stations, Fort Collins, Colorado. There's the phone number if you want to call it. And if you make that phone call, you get about 2 minutes worth of WWB radio time signals.
Universal time. National Institute of Standards and Technology time. This is radio station WWB, Fort Collins, Colorado, broadcasting on internationally allocated standard carrier frequencies of 2.5, 5, 10.
Anyway, I just made the phone call so you can write down that number, or you can look it up on the internet. So in case of an emergency, if you're doing video and you have an equipment failure, you can get out your cell phone and you can actually call WWB and get about 2 minutes worth of times and do these call outs if you have a voice recorder as a backup. And it's been done before, but we generally don't use this technique anymore.
Richard, how much of a, so I'll forget to ask it later. How much of a latency sort of delay is there with the time signals coming over your phone?
Probably on the order of 1/10 of a second.
Oh, that's not bad.
It's not too bad, but we like to be more accurate.
Mhm.
And delays vary. It could be 0.2 of a second. It could be right on. It just varies.
Okay.
Okay. Now, video recordings provide the best precision because each video frame at 30 frames a second, NTSC is 0.033 second precision. If you're in other countries like Europe or Australia, they use the PAL method, the PAL standard, and that's 25 frames a second or 0.04 seconds per video frame. And the good thing about videos, you can play them over and over again, like the one I just showed you. And GPS time insertion really simplifies timings. It is so much easier. Trust me. Those timings on the tape recorders, that was hell trying to figure out those times. Okay. Here's how GPS time insertion works. On the left, you've got your telescope and your video camera hooked up. Your video camera goes into the time inserter, which picks up the GPS satellite signals through this antenna and sends the information to your camcorder or your video recorder or your digital recorder and overlays the time right on the screen. It's a beautiful system. And these units, Iota sells one called the Iota VTI. I have a slide on that later. They average about $250, the time inserters. Bruce Berger knows about this. Okay, here's a camera that a lot of us use. It's called a RunCam Astro camera, RunCam Astro. This particular version of this camera software was designed for Iota as we approached the company that made them, said, look, we need a custom version of this camera for our use. And they did it for us. And they did this for several years. Unfortunately, about a month ago, they stopped doing it. I don't know what's going on here, but that's the situation. It's a very inexpensive camera. The adapter is about $100. So your total investment is under $200 for the camera and adapters. You can still buy the camera, it just doesn't have the software that we use. And it's hooked on the back of a telescope with a focal reducer. So it looks like this. Here's your RunCam camera, your adapter to the focal reducer. And you want a wide field for asteroid occultations because you're having fewer pixels pick up the stars so they appear brighter. This is a consequence of the physical properties of the chip. So it makes the star appear brighter, which is what you want. Here's one of my setups. I've got a 4-inch telescope, the GPS time inserter on the bottom. And by the way, that NASA sticker helps me get through airports. They look at this thing funny sometimes. Here's the GPS antenna. Here's the camcorder. Here's the batteries. Very portable, fits in a suitcase. I always carry it on board. Never check your telescope into baggage. You just don't want to do that. Okay, the Iota video time inserter, Iota sells these things. They're about 250 bucks. It's on the occultations.org website, so you can check it out on your own. It's a very good unit, and most everybody uses it. Okay, asteroid occultations. This is the geometry of an asteroid occultation. You can see the asteroid shadow projected on the Earth. We have observer station perpendicular to the shadow, moving path, just like a lunar occultation. And that's what it looks like. So here's exactly what happens with an asteroid occultation. Asteroid moves in its orbit through space, passes in front of the star. This could be real time. Seven or 8 seconds, that's a real-time asteroid occultation. I've done them as low as one occultation I got a couple of months ago was 3 video frames, and I almost didn't see it when I was watching the video, but I reduced the data, I saw a 3 video frame disappearance. This is for the asteroid Apophis, which is supposedly, allegedly was going to make a close approach to the Earth several decades from now. Anyway, there's the asteroid occultation. And this is the CCD drift scan technique of an asteroid occultation. This takes a little bit of time of setting up. What you do is you have a CCD camera, not a video camera. You're taking a single exposure and you're letting the star trail during the exposure. In this case, it was about 4 minutes. So the start of the exposure in the upper left-hand corner and the time of the exposure was known because CCD cameras import the information to your computer. And the star disappeared about 2 minutes, not quite 2 minutes later. And you see the drop in brightness of the star. Again, the star is trailing. The motor drive is turned off on the telescope. Star reappears, you know that time. Here's the end of the recording down here. And with these numbers, you can get the duration of the occultation and the times. Very, very useful technique. Not too many people use this anymore. Jim Young came up with this technique back in the early 2000s. And on the right-hand side are several other examples of this technique. You can see the star disappearances, the dimming and brightness of the stars. Okay. Again, not really used that much anymore, but again, a very useful technique. This is an asteroid occultation from 30 years ago of the asteroid 216 Cleopatra. The path occurred over the northern United States, as you can see from the diagram below. And these are the occultation chords determining the shape of the asteroid, would kind of shape like a cigar or a dog bone. Okay, this is 30 years ago. This came out of Sky and Telescope magazine, this particular chart, this particular image. And this is the first time this asteroid was ever observed. So that's kind of an unusual shape for an asteroid. Not necessarily unusual, but it's very lucky to catch it at that orientation. Remember, an occultation is of the size and shape of the asteroid at that time. These things rotate and they have different, weird shapes and sizes. And we're very lucky to catch it at this particular orientation. Now, 8 years later, Stephen Ostro made these radar images on the bottom part of the screen of the same asteroid, Cleopatra, and came up with the same kind of a shape. Up above are 10-meter telescope pictures, direct photographs of the asteroid with the Keck telescope. And you can see this is very small field of view, 0.8 of an arc second. That's a very, very good picture for, Earth-based picture. And these guys, when Ostro published this report in a journal, they never mentioned Iota's discovery of the shape of the asteroid, largely because it was unknown, being in Sky and Telescope magazine, not really a professional type journal that they would search for. Here's more shapes and sizes of other asteroids from occultations. Cleopatra in the upper left-hand corner, Hertha over here, and the gray colored model here behind it is the shape of an asteroid determined from light curves. It's called a light inversion model. On the right here is a double occultation, two bodies. This is 90 Antiope. This was 10 years ago. I'll more about this one. On the left here, lower left, 54 Alexandria. This is a long occultation, approximately 1 minute. I was in on this one somewhere. My name's on here somewhere. And I remember this one, it was so windy where I flew to somewhere, landed, and it was just so windy. I had to find, I couldn't find a building to hide behind, so I hid behind my car to make the observation, to block the wind. This observation down here, lower center, 22 Calliope, was made from Japan. It had a satellite, and observers were stationed to try to record the satellite, and they did a great job over here, Calliope 1. This is again from Japan. We have a large number of observers in Japan, as well as Europe and Australia. Okay, asteroid occultation. This is what happens as the shadow moves across the Earth. And observers 1 through 6, observers 2, 3, 4, and 5 should see an occultation. Observers 1 and 6 will probably have a miss, but that depends on the prediction of the path. The path could shift up or down as indicated by the dashed lines. So back before the Gaia catalog came out, this is what we had to deal with, path shift errors. All right. So here's an asteroid. I just took this asteroid out of a book. This is a satellite photo, sorry, a spacecraft photo. And here's an occultation, observers 1 through 5. And as you can see, when they plot the position, the ground position versus time, observers 1 and 6 have no occultation. Observers 2, 3, 4, and 5 do have an occultation, and this provides the size and shape of the asteroid. Observers 1 and 6 are very important because their misses put limitations on the size of the asteroid. So we need those, the first miss. If you have the second or third miss, we really don't care about your observation. We just want the first miss. Okay, another video over here. Let me try to get to it. This is an occultation of a star from 2019. Let me see if I can get to it. Again, pardon me for taking a while to get this video visible.
No worries at all.
Yeah, okay. Let me stop share. Let me go back to share screen. And okay, let's start over. We all see the video now?
Yep.
Okay, this is a video of 55 Pandora. The target star is right here in the center, and it gets covered up for about 5 seconds. Asteroid occultation. And if you look closely, it's kind of hard to see. You can see the asteroid very faintly. We can try that again. And again, GPS time insertion on the bottom of the screen. Let's try this again. I don't know if you can see the asteroid. It's kind of a noisy video, but you might see the asteroid, you might not. Okay, that's that. Okay, for that particular asteroid, let me get back to the screen again. Okay, we should be back in PowerPoint.
We are.
Okay, that asteroid video I showed you, occultation. Again, a very rapid disappearance of the asteroid, of the star. You can see just 2 or 3 video frames. This is typical. A 0 light level during the occultation, and coming back out, 2 video frames to come back. Here's the size and shape of the asteroid from the occultation over here on the right. And on this one, they had, I don't know what, 15 observers, 14 observers. Again, you can see the misses up here. Number 2, number 1 had misses. This puts limitations on the size of the asteroid. Number 3 out here, we really don't care about it. We include them in there just to be nice in the publication. this is all online. So, okay, next slide. Now, asteroid occultations have the opportunity for discovery, in particular an asteroid moon, as demonstrated in this animation. You might have a miss on the asteroid, but you might see the moon pass in front of the star momentarily, very, very short occultation typically. And it turns out 3 months ago, back in May, a moon was discovered by an asteroid by 2 observers in Australia, our very well-known colleagues, Peter Noseworthy and Dave Galt. And on the left-hand light curve on the top, if you look at it, the light blue curve, here's the drop in brightness to the main asteroid, then it comes back out. A few seconds later, here's the drop of the moon right over here, and then comes back out. Dave Galt recorded the same thing. Again, the reference star on top is a reference star video, a reference star just to make sure there's nothing funny going on with the atmosphere. Typically, variable star observers have check stars and reference stars in their observations. Okay, now it was confirmed, three weeks later, it was confirmed by 2 observers in California, Dr. Richard Nugent and Kirk Bender, and they had the same kind of video. The main occultation of the main body and the secondary occultation of the second body for both observers. So either this is an amazing coincidence or it's a real discovery. So here is a profile of both occultation observations in Australia and California. The upper one is Gault and Noseworthy. You see the main asteroid here and the secondary body. And this secondary body, this is a guess, but it's a pretty good guess based on the length of the chords. And Nolthenius and Bender had a better observation of the secondary body because they were spread out a little further apart on the ground. And the same thing with the primary body. So they got more realistic shape. Again, this is a guess. There's only 2 observations of the shape. Who knows what's going on over here? So this is a satellite discovery. Now this is a preliminary satellite discovery. Iota offers an award for discovering an asteroid moon by the occultation technique. It goes to amateurs only. The amount of the award is a one-time award of $4,000. It's open to amateurs only, no professionals, and the satellite discovery must be confirmed by other methods. In other words, not another occultation. And if confirmed, we'll, of course, communicate the discovery to the IAU. Now, I'm an officer of Iota, been an officer for 25 years, and we had a long talk about this by email and over the phone 3 months ago. So what are we going to do with these guys? Well, we have to wait till it's confirmed by another method, such as photoelectric, maybe one body eclipses the other by looking at the light curve, or maybe a professional might use a big giant telescope, that we'd love to have in our backyard and take some direct pictures or do some other technique, or maybe radar. So it has not been, fully confirmed, but we're pretty sure they discovered it, but not fully confirmed as a scientist would require. So keep this in mind if you want to get involved in the occultation business. $4,000 is a nice chunk of change. But it looks like if this one's confirmed, the Australian guys are going to get it. Okay. This is an occultation of Pluto, occurred 3 years ago, and it went over the United States. Now the center line, the blue line, is the predicted center of Pluto's, the center of Pluto across the Earth. The purple lines, the dashed lines, are this is the size of Pluto from here to here. The solid gray lines on either side of the dashed lines is the error margin in the prediction of the position of Pluto. So there's a slight little error, but not much. So we did this occultation. I did it from West Texas at my personal observatory. David Dunn did it from, I think he went to Houston. I'm not sure. Here's the light curves. As you can see, they're pretty noisy, but there does show a gradual disappearance on Dunham's light curve and mine regards to Pluto's atmosphere. We have the total occultation over here, and then coming out, the same thing. I remember that night, the seeing conditions weren't that great, so my video is kind of nasty looking. And I'll tell you, trying to figure out the time of the occultation here, where the atmosphere ends and Pluto starts, it's pretty hard to figure out this amount of video frames, because this occultation lasted several minutes. But we can stretch out these light curves and look at individual frames. Okay, as a result, here's the size and shape of Pluto during that occultation. And we only had 13 chords. Now, why did we want to do an occultation of Pluto? Because the atmosphere was discovered, what, 30 years ago, 35 years ago? Well, another occultation of Pluto occurred in 2020, and observers, our Middle Eastern section, Iota Middle East, led by Altero Porlo, they measured an occultation of Pluto also and found that its atmospheric pressure was about where it should be. They do this to measure the atmospheric pressure, and they compare it from occultation to occultation, and especially to the New Horizons flyby in 2015 to see what's going on with Pluto's atmosphere. So this is one advantage of continuing to measure occultations. And they published this paper, came out just recently. So he made this presentation at our Iota meeting in July, and did a great job. Okay, now let's move on to the mighty mini revolution. What is this? Scotty Degenhardt, one of Iota's observers, one of our great observers, came up with this technique of creating a telescope system based upon a video camera, a piece of PVC, and a piece of a binocular. He calls it the mighty mini. And this is a very powerful system. As you can see, you make it by taking part of a binocular, unscrewing it, getting yourself a couple of pieces of PVC, spray paint it black, a little adapter for your video, and you put it together. And you put it on a tripod, and voila, you've got a video system, a portable telescope. Now, why do you want to do this? Very simple. It's hard to get occultation observers, a lot of them out in the field. So if you have, say, 10 of these, you can lay them out one at a time, say 2 or 3 miles apart on the road, and you've got 10 stations. The setup of these things and the pre-pointing in the sky is a very difficult thing. It takes a lot of planning, but it can be done. And once you've done a few and made all the mistakes like I have, you can eventually start doing it and get good at it. Scotty's first really successful event on this one was 135 Hertha. This is back in 2008. And he had 14 stations set up and each station had a hit. He'd set them up. He'd drive to the next one, set the next one up, pre-pointed toward the field of view. Again, no motor drive. The Earth would rotate and the target star would rotate into the field of view at the time of the occultation. So the setup on each one was very, very, very tedious. And you need star charts, you need times and all that. Depends on when you get to your particular site. So this is a great little technique for, a lot of people use this technique. I've done this technique several times, but I've never had a hit. I've had telescope systems that work perfectly, but no shadow. So, it's a hit or miss thing. Anyway, it's a good technique. Plus, it's inexpensive. Now, in 10 years ago, this is a very good occultation. 90 ATMoB went over the United States, in particular Northern California, in July. And if you know anything about California, the weather in California in July is basically totally, completely clear. It's pretty much almost a guarantee of clear skies. And this is a bright star. Up here in the upper left-hand corner, magnitude 6.7. So a lot of people had these little mighty mini systems set up, plus other telescopes and other systems set up. And we had a big observation campaign of over 50 stations. Now, a few days before the occultation, we wanted to know what the orientation of the two components were of this asteroid. So we got these pictures from the Keck telescope in Hawaii. They were nice enough to take these pictures and send it to us. So when we made the occultation, this is the result. Over 50 observations, 50 people on the ground, a bunch of misses, which is good, on both sides of the occultation, all planned long in advance to do this. Everyone had assigned stations, and you can see the detail in this, in the size of the asteroid and the shape of the asteroid. Very, very good detail. And this resolution with this technique, we got 300ths of a second of time, video timing accuracy. We're looking at maybe less than half a kilometer in resolution. Okay, so this technique with a $250 telescope compared to the Keck telescope, you can see the results here. These telescopes here on the left, these are 75 million bucks a piece. How many people have that kind of bucks? I'd rather use this one. Of course, I'd love to use this telescope, but this is the comparison. Look at the precision versus what their direct photographs are. Okay. If you want to find out about asteroid occultations, we have a website, asteroidoccultation.com. This is maintained by Steve Preston, Iota's president. And you just go to this webpage and just click on the right-hand side and look at your particular maps, the visibility area. You can look at here, Russia, Europe, South America. Here's a couple of the United States, Canada, South USA. Just click on one. You'll get something like this, a map like this. This particular one is September. I can't see my screens out of the way here. September
15th.
15th. Okay, this is next week. Starts out in Southern California. Actually starts out in Canada, upper here, upper right. Goes down lower left through Southern California and crosses the Earth and gets off the Earth. Now the times at the top of the page here, 8:32 and 8:15 is the time it spends covering up the Earth, the asteroid directly in Earth. So if you're like located in, say, the Lake Superior area, you're going to be looking at a time of 8:46 or 47 over here. By the time you're in California, 7 minutes later, it's now 8:55, 8:56. So this tells you about when you need to set up. And realistically, you want to measure on at least 2 or 3 minutes on either side of this window to make sure you catch everything. You might catch an asteroid moon. That's possible. Here's another one. This is later this month. This is one of the satellites of Uranus. Hence, the prediction error there's a prediction error quite large, covering a couple 100 miles either way. This occultation, I can't see the screen due to the Zoom cover up
It's
here.
like the 28th.
September 28th, later this month, thank you. This is a 13.3 magnitude star. It's a faint star, but this is a good occultation. I might try it. I live down here, Central Texas. You might try it up there in the Boston area, Northeast. That's possible. So keep that in mind.
Richard, a quick question while we're on the slide. What causes that largest uncertainty? You would have thought that the moons of Uranus would be well understood.
Well,
as far as
that's what one would think, but they're not observed that often where the orbits are they're so far away, a tiny like 2 or 300ths, a tenth of a second error in position could result in a huge path shift error on the Earth. I'm not sure that the positions are known precisely and that they're measured all the time. But the occultation will definitely narrow down the position once we get it. In fact, not only do we determine size and shape of asteroids or moons of the planets, we get a very precise position based on basically the position of the star. Now that we have the Gaia catalog out, we get asteroid positions to 1 to 10 milliarc seconds and better. And that is reported to the Minor Planet Center. It updates the orbit of the asteroid. And it's especially important for near-Earth asteroid crossers, NEAs, which we did one a couple months ago. So it's another not so well-known benefit of asteroid occultation. Okay, once you, okay, another website for asteroid events. This has Google Maps. This is Derek Bright's website. He basically copies everything from Steve Preston's website, asteroidoccultation.com, and you get a Google map. You can tap on Google Map and get your real-time Google map of that particular event, something like this. So you can really zoom in. This is a regular Google map. You go satellite, you can zoom it around, and you get the center of the asteroid path, which is the green line. This is Central Texas. You have the size of the asteroid shadow on the ground, the gray lines, and the red lines indicate the error in the position, the path error, which is not too bad. They're actually much better with the Gaia catalog. This is before Gaia Data Release 3 came out, so this got about a 10% error. So this is a very, very good map to use. I use them all the time. This is the last slide. Basically, Iota, we want you. Join us. Our websites are asteroidoccultation.org, asteroidoccultation.com, occultations.org. I don't know if you can see me. We have a manual here. It's a free download off the website, the Occultation Manual, edited by yours truly. We have like 10 authors, and it came out 13 years ago. It's got needs some updating, but basically the techniques, the methods, and the theory is very good in this book. Just bragging here. Got lots of diagrams and figures. So consider it's a free download. Take it to your print shop, make a print copy, but just don't sell it without our permission. Okay. And with that, I take any questions or comments or ideas. I'm wide open for questions.
I have some questions for you. When you see me look away during your presentation, it's because I'm just writing down questions. I was impressed when you said that the accuracy can be as much as 3 milliarc seconds early on in the presentation.
Right.
That's pretty impressive. That is the resolution of some double stars you guys can measure, right?
Yes.
Folks can measure 3 milliarc seconds. That's impressive. And I was about to ask about the diameters of larger stars, and then just no sooner did I finish writing it down that you would put it up there. I know occasionally when Aldebaran is occulted by the moon, some observers have reported they can actually visually see the dimming of the star.
Yes.
Because it's a pretty large star. And that's pretty cool. And then I was going to ask about, I don't suppose that people in their backyards could do this because I think everything is just too faint. But do the big observatories, when they, for example, if there's a big observatory armed with a spectroscope, lots of sensitivity, and they're say looking at Pluto's atmosphere, do they grab a spectrum of that to try to analyze atmospheric composition?
I imagine they do, because the atmospheric pressure calculation, I'm not exactly sure how they do it. This is another field I'm not really good at.
Yeah,
I'm sure they do something else besides the occultation, because the spectra of the atmosphere of Pluto is now, because of the New Horizons flyby, we've got a much better properties of the atmosphere, so we can see how it changes over time, if at all, by the occultation technique, at least to some degree of precision. I'm certain they do spectrum of that. That's probably a good idea to do spectrum. Yeah, good point.
Even just the idea that Pluto is currently moving away from the sun, and as it gets colder, one would imagine the atmosphere would shrink, if not completely disappear. So I would imagine that that's something you could do with, without the use of a spectroscope, just looking at the way the star dims as the atmosphere occults it first.
Oh, definitely. The occultation technique reveals quite a bit.
Yep.
Quite a bit here, yes.
So that might be a way to study Pluto's atmosphere from here, as far as, again, like I said, when it gets further away from the sun and the atmosphere condenses out basically because it's getting colder, you'd probably be able to measure that. That's pretty cool.
Yeah, at higher levels above the surface of the planet, the atmosphere is thinner, just like our atmosphere. So the dimming is very gradual. Then it gets, the dimming changes. So actually it gets fainter. You see the drop in brightness. And then, of course, the total occultation and the same thing coming out in the reverse. So I'm not exactly sure how they did the atmospheric pressure thing, but they've got to figure. I've not read that paper entirely, but I probably should read it.
Well, I always like to watch occultations of stars by the moon, just through my own telescopes. No science going on, just for the pure pleasure of it. And I've always marveled at how quickly the stars are snuffed out by the limb of
It's
the
a
moon.
lights out thing. Definitely. It's lights out for most of them. Yeah.
Fantastic.
Yeah.
And I always think about how early astronomers watching occultations surmised from the observations that the moon had no appreciable atmosphere, because even they knew that, just like when the sun's setting and you're looking through subsequently deeper and deeper layers of Earth's atmosphere, if the moon had an appreciable atmosphere, you'd see the same effect. And since it's not there, except for big stars, which are just kind of, taking time to cover the disk. I'm always impressed at how quickly an occultation takes place. And I know bright stars are rare, but if amateurs have a little bit of aperture, whether they're doing science or not, you can watch relatively faint stars being occulted by the moon, especially when you're up against the dark limb.
Exactly.
So I like to do that. And as I mentioned, I've only seen one grazing occultation, and I wasn't even prepared for it. It was serendipitous that I just happened to be looking at the moon and watching a star, and I wonder sometimes as it approaches the limb of the moon, gosh, is that going to be a miss, or is it going to be a hit? And I was surprised that I can't even remember what star it was. It's in my notes somewhere. I was surprised to see it disappear and then pop right back out again. And I was like, oh my gosh, I'm on the graze line. And it did. It went in and out a few times. It was pretty impressive. And I imagine, of course, it depends on how far away the moon is and and how high the mountains are. But the graze path, what's an average, if you wanted to put yourself in a graze path, that's got to be super narrow.
It is. We're talking a graze path typically is 2 to 4 kilometers.
Oh, that's all, huh?
It's not much. You're just talking if we know in advance, like the southern limb of the moon, the mountains are higher than the northern limb. We have a longer, wider graze path, like 5-6 kilometers. But the northern limb is much. The mountains aren't as tall, so 2-3 kilometers will do it. Yeah, it's predicted in advance. And if you're looking at a particular, any basic planetarium program, you just kind of make the moon move across the. You can tell which direction the move is going, whether it's going to be a graze or a total for your area or particular location. Very simple to do. And
I imagine with the Gaia data, I know you were talking about really knowing the positions of the stars. I guess that would take a lot of the error out of that. Or is the limiting factor the uncertainty in the moon's orbit, that graze path, or is that just the physical size of the mountains of the moon?
Well, we know the physical size of the mountains from these radar missions, the LRO and the Japanese Kaiguya mission from the 10, 12 years ago. And we know the position of the Gaia stars. We don't really care about lunar occultations anymore because we got the lunar limb down, pat to like 100 meters.
Yeah, I figured. As a matter of fact, I was like, what's the purpose of the observation of watching a graze on the moon?
Well, lunar occultations, we tell new people this is just for practice. This is what happens. It's practice. You set up. You can find the moon. That's pretty easy to find.
It's an easy one.
An asteroid targets are a little bit more difficult to find. Just practice to get going. The asteroid occultations, the position of the asteroid is just as important as the star to get an accurate position. But with you see the various chords. I'll go back a couple of slides here. Take for example these chords. We've got like this particular chord here. You just take the center, you average the chord to get a geometrical center, and this is done by Dave Harold in Australia. He does this reporting to the Minor Planet Center, and the center time here, to a fraction of a second. You can get a very, very good astrometric position, which you report to the Minor Planet Center. And there's other factors to consider also. There's a gravitational deflection of light of the star, which has to be corrected for from the sun. It's different from the asteroid and the star, believe it or not, because the asteroid is much closer, and its light does not necessarily. Anyway.
Wait, say that again. Say that again. What causes the gravitational deflection?
Of light from the sun. It has a pull on light almost 180 degrees away from it. There's a little bit of pull. It's maximized near the center, right up against the limb of the sun, but it fades away as you get further away from the sun.
Sure.
Calculable effect there. And Dave Harold computes this. It's very, very small, but he computes it. It could be 1/10 of a milliard second.
And that's measurable, huh? That's fabulous.
It's calculable. It can be calculated.
Okay.
But you take it into account, even though you don't measure it. In other words, we can measure the gravitational pull of a galaxy on us here on Earth. We couldn't measure it, but we can calculate it.
That's great.
This is
That's
like double stars.
That's fantastic.
What is a binary star? How far away do they have to be from each other? How close?
Hey, everybody, I only have 5 more questions to ask. So get your questions ready. Of course, the next thing I just wanted to make a comment on the timing techniques. I remember back in, it had to be the 70s. And I remember looking through a pair of binoculars with a pair of stopwatches in my hand. And I was going to try and time some asteroid occultation of a star using stopwatches. And I just remember how foolish I felt trying to, but I guess fortunately we missed the occultation. So I didn't have to worry about human reaction time and that sort of thing. And bobbling time stopwatches, but I can only imagine. And I thought you guys were still perhaps using the WWV signals on video, but you guys are way ahead of that. 2 occultations that I wanted to ask you about, because I don't think anybody saw either one of them back a while ago, maybe about, I'll bet 10, who knows, 10 years ago, Regulus was going to be occulted. And
March of 2014.
2014. Okay, almost 10. Almost 10. It was like going to be about like 6 seconds, right?
Right.
Where Regulus was going to disappear from view. And I don't think anybody witnessed that. I think the whole path was clouded over.
It was. I was going to fly up there and do it, but unfortunately, a week before I was in a major car accident. I was really injured. I couldn't make it. But luckily, it was cloudy, so I didn't have to worry about it. I
was going to drive to the New York area just to witness him. I had no tech, nothing to record it, but I just wanted to watch it happen. It would have been pretty cool. Another one back in February of 2019, the Sirius was supposed to be occulted by an asteroid. And
like Arizona to Canada. Yeah.
And I know it didn't happen in Framingham, Massachusetts, because the crudest of setups, I literally took my iPhone and pointed it out the window and just took a long video of maybe 10 minutes on either side of the predicted time. And I saw no disappearance of Sirius, but I thought that would be pretty fun. And then that makes me go down to where they, where did I put this? When what was my question going to be? When the observers saw the occultation by an asteroid, and then a few moments later, the occultation of the moon, that super sharp spike. Were they watching that on a video feed? Did they actually see that with their eyes?
If it was bright enough, if it was more than say 2/10 of a magnitude, they probably could have seen it.
Wow, that's pretty cool. That must have been pretty exciting. That's fantastic. And
there's strange things that go on during occultations that you won't know about till you look at the curves, the light curves, and analyze the light curves. Sometimes the star is drifting in and out of focus. This is the atmosphere doing this, and you see a blur. It happens. Wind causes really weird things going on with occultations. It looks like an occultation, but this target star is shaking around so much, the aperture using to record it just can't keep up with the wind shaking the star around. We have these programs that use it. So it creates really strange things. You have to know when the occultation is, what's a wind occultation or a real occultation. It's really a lot of things here. A lot of things can happen. A lot of things can go wrong. I've made every mistake there was and more. And we've learned over the years, there's really no more new mistakes. The same mistakes are just repeated.
It's probably all covered in that manual.
Exactly.
And, one last question, Rich. With the equipment you guys use, the relatively small aperture, easy to put together sort of stuff. How faint of a star can you watch being occulted, where you get meaningful data? I only ask it because I've mentioned to folks in the past, first, bright stars being occulted by the moon, relatively rare if you just want to see something happen. But if you've got a little aperture, especially like I said, when there's a waxing crescent moon in the evening sky, and you can see that dark earth shine lit limb, man, you can watch some really faint stars disappear. They don't have to be super bright as long as your telescope can see them. I know with cameras nowadays, man, you look at some of Mario Mata's images, and I know they're long exposures, but he's reaching well into the magnitude 20 range. And I imagine that, some of these CMOS cameras nowadays can really eke out some pretty faint stars. I'm just wondering if there's a limit to what you guys get away with.
Well, the orange colored camera I showed earlier, the RunCam camera,
Yep.
through my 8-inch telescope, I live in a relatively dark sky where I live in Central Texas. I can see down to magnitude 12.5, 13 with an 8-inch telescope, my Next R8. With my little 4-inch telescope or my Questar, I can see down to magnitude 10 or 11 with that in my sky, maybe a little bit fainter, depending on the maximum, whether it's a red sensitive star, a late time star, an early time star. The cameras are red sensitive by default, so they see like red dwarf stars are much brighter than like A-type stars, bluer stars. That's a factor. But we can see pretty good. And this orange colored camera has got a feature. It's got a little handheld push button thing that on a menu, you can actually do a integration video. You can combine frames together 2 times, 3 times, and 4 times. You can combine up to 8 frames a second, and you get maybe 3 frames per second, integrated to reach fainter objects. I think you don't do that because you lose time resolution. So, but it can do it. And these cameras are amazing these days. My digital single lens reflex camera, these chips are so sensitive, you can set it for 25,000 ISO, 10-second exposure, you can see 13th magnitude stars.
Sure. So, so my last question / comment is, goes back to what we have at our Westford observing site. By the look of this, measuring occultations is a mobile, you require mobility, because otherwise you have to wait for the asteroid to come to you. What could we do with our fixed telescopes up in Westford, Mass, as far as occultations go? Is there any citizen science we could integrate into those systems?
Well, you could do lunar occultations. That's easy to do.
Yep.
The moon's pretty big. It covers a lot of stars. And just check the website, asteroidoccultation.com. Try to find one that comes over your area. Probably 2 or 3 times a year, you'll see some coming over the Northeast area, Massachusetts, Boston, and so forth. So keep that in mind. Keep that in mind.
And a miss isn't necessarily a bad thing, is it?
No. There's I have a permanent observatory located in Fort Davis, Texas. And I've done the Pluto occultation I did there 3 years ago. I've done some occultations there. It's 400-mile drive from my house, so I don't go out there just for an occultation. I go out there to do other stuff. But I've gotten on planes many times and flew to get these occultations. So we're an all-volunteer Army. Excuse me, an all-volunteer Air Force, because we're on planes all the time.
Well, I like the asterisk about what Iota really stands for.
Oh yeah, that's
something about being away from home for a long time. I'm out of town a lot. There you go.
Well, there's lots of Iota jokes on out there, so that's true.
Well, good news, members. I've come to the end of my questions.
I've got a question.
Is that Joseph? You have to just unmute yourselves.
Yeah, I just had a question. I remember it was maybe 30 years ago, maybe 40 years ago, there was an occultation by Saturn that was used to probe the rings of Saturn. I was just wondering, I remember observing it visually. I was wondering if you have any information about that or remember it.
That was 28 Sag, right?
It was 1989, sometime in 1989. I did not see it, but I know Paul Maley, who was a friend of mine living in Houston at the time, he actually recorded it and he saw it. I'm not sure what came out of it. We're talking 1989. Video cameras are not as great as they are now. He might have done a video. I don't have to go talk to him. I'm going to be seeing him in Antarctica. We have a trip to Antarctica for an eclipse this December. I'll ask him about it then, or I'll give him a call. He lives there.
What I remember is seeing, maybe it was in Sky and Tell, a picture of Saturn with very detailed rings, ringlets, similar to what you're getting from the orbiters now, but that wasn't available at that time from Earth. So,
Joseph, I was taken on that. That was 28 Sagittarius that Saturn passed in front of. And what I remember that impressed me the most about that occultation was when Saturn, when the starlight passed through the crepe ring, the innermost ring to the planet. I thought for sure we would just see the star the whole time because it's such a faint, gauzy little ring. Man, that brightness was jumping up and down like crazy. Suggesting that we were looking at ringlets that are, had physical dimension in that, otherwise bland sort of ring. It's pretty cool to see. You don't get that very often.
That was a good observation. Yeah.
It
Well, that
was.
proves the ringlets and the multitude of rings, which I think Voyager had already gone by. Well, that was about pretty close to the time Voyager did the flyby,
Mhm.
late 80s. Yeah.
Yeah, pretty close.
So
Alba, did I see your hand up?
Yeah, a simple question for you. A lot of us are investing in CMOS USB cameras, and I'm really impressed with what you managed to do with NTSC. But is there a technology that would allow us to get the same kind of timing accuracy with a USB 3 CMOS camera?
I think so. I'm not an expert on this. At our last meeting, there was a couple of presentations in which they talked about this, these cameras and timing. The Iota website has got a list of their annual meetings. If you look at the annual meeting for this year, 2021, you might see a presentation on it. I write up the minutes and the summary of the meetings. I remember something about that. They were talking about the timing, doing something like that. If you contact me offline, I can try to find out and send you some stuff on it. Because I'm not an expert on the cameras. These cameras, I know video cameras, these QHY cameras. I don't really know much about them. Yeah,
I remember
QHY.
I was really interested in trying to do some occultations, but I'm in the CMOS USB camera land. And I remember reading there's some complications with timing because you can't guarantee the exact timing of frames when they land. And you can turn on time stamping, but it's not necessarily accurate. And I saw an interesting approach where someone made an optical time inserter. So with the larger CMOS sensors where you have some real estate, they actually have an LED that's connected to a GPS pulse per second.
Mhm.
And the LED gets focused through a lens to project a spot on the sensor. So you actually have an optical spot that comes and goes, but that's pretty involved.
Yeah, Art Olson knows about that things. He'd be the one to contact, Art Olson. I can get you his email.
For a short while, QHY did produce a CMOS camera that had an internal timing circuit with the integrated GPS, and it would guarantee an accurate timestamp, but I don't think they make that one anymore. I'm not sure if they still make it, but it was pretty pricey.
Yeah, those cameras like $1,000 or more. Yeah, I know that.
Somebody also, Bob Tube, was that your hand up before? Somebody just had a hand up. Just unmute yourself and go ahead and ask.
Is there an advantage to
waving
going
around.
to higher frame rates?
Say again, Michael?
An advantage to going to higher frame rates?
Yes, a higher frame rate would give you better precision, timing precision. Most definitely, yes.
It's like that's the temptation with CMOS is you can make a region of interest and you can easily get 200 frames per second,
Right.
but you
Right.
got to be able to time it accurately, because if it's like comes in chunks and there's gaps in between, it can make trouble when you're trying to lay out the frames in time if it's not
Yeah,
a
that's one of the
consistent.
issues. That's one of the
data.
issues with those cameras, yes.
That's the nice thing with video and analog and the broadcast standards. The timing is very reliable, whereas digital CMOS over USB, it's not necessarily solid or regular.
On the
Even
Iota discussion group, there's a lot of talk about those cameras and what they're doing, and I've not really followed it that closely. I keep it simple. I use a digital video recorder, 30 frames a second, regular camera. I keep it simple. And it's GPS time inserted. It works. It works. But a lot of people say, I just have to use a computer. I don't want to use a digital video recorder. Well, go right ahead. But there's a lot of complications and there's all kinds of, it's complicated. It's kind of like taking one medicine, getting a side effect, take another medicine for the second side effect, and so on. Either way works, but if you follow the Iota discussion group, you can get on the Iota discussion group. Go to occultations.org. It'll show you how to get on. You can look for old messages and you can read about it, what they've been doing. I'm not an expert on that. I just remember reading about it. So occultations, the equipment alone could be a whole subject. We have presentations on equipment every year at our meetings, our annual meetings, and it gets very complicated. Also, we have like 4 or 5 different software programs to reduce the data. We can analyze noise and where you would never think there's an occultation that could be brought out by analyzing the noise levels and so forth. It's really, really kind of very sophisticated. This is the 21st century. Of course, you have to be at the right place at the right time.
That's what it's
Now,
all
when
about,
we were all
right?
younger, you walked outside and you saw a flash of a shadow going across the ground. You look up in the sky, you see an airplane just past the sun, just went in front of the sun. Now, if you came out 10 seconds later, you would have missed it. Or if you're 100 meters down the road, you would have missed it. So you got to be at the right place at the right time.
Is there any value other than the pure beauty of it, of timing occultations of, like, say, the space station crossing the sun or the moon? I know there's a website that gives a pretty accurate predictions for that. There can't be any science that can come out of that, is there?
I wouldn't think so, but it sure is pretty cool.
It is cool to watch.
Really cool to watch. Yeah.
That
A lot of preparation. It's really cool.
Transit Finder is a great website. You just filter up the sun, and I tried it. It's remarkable. Literally the moment they say it's going to be there, it crosses the sun, or the moon.
Oh yeah.
And if it's a central, central transit, it lasts, gosh, a second and a half maybe. Depends on how far away they are, but they're fun to watch. They're really fun to watch.
Yeah.
Anybody else have questions? I'm only on speaker view, so I can't see everybody else. But just go ahead and unmute yourselves and ask away. Well, let me do this then, Richard. I'm gonna take back the screen sharing so I can put the last slide up for the meeting, and then we can close that out. And normally, folks stick around for a while. I hope you can. I know you're an hour earlier than we are. But maybe you could stick around for a little while and just chat with us. Let me see if I can go back to sharing the screen. Let's see, one more slide over. So let me just finish up the meeting. So next up is our next ATMoB board meeting on Thursday, September 23rd at 8:00 p.m. And our next monthly meeting will be on Thursday, October 9th, 2021. At 8:00 p.m. I always open the doors a little early for both of those meetings. And I'll send out Zoom invitations to everybody the Sunday before. The board meeting, of course, is really where you just hash out the nuts and bolts of the club. And folks are invited to have a kind of a listening, watching experience, not necessarily contributing.